Math 2415, Chapter 10, Section 2, Cross Products. Cross products involving I, J, and K. As was brought up at the end of class today, there was something I meant to mention in this section that I did not get to before we started section 10.5. That particular thing, which I believe involves homework questions number 10 and 12 from the homework for section 10 this isn't 10.2, this is 10.4. Cross products is chapter 10, section 4. But I believe homework questions 10 and 12 involved cross products involving I, J, and K. Now, technically speaking, you don't need me to tell you what I'm about to tell you if you remember that I, J, and K are just the unit vectors in the X, Y, and Z direction. Component-wise, the vector I in 3 dimensions is 1, 0, 0, the vector J is 0, 1, 0, and the vector K is 0, 0, 1. So you can find the cross products of any of these just by using the cross product formula. But I want to show you two things. Number one, a way to calculate the cross products without actually using the cross product formula. And number two, a way to remember the cross products of any combination of I's, J's, and K's. One thing that we can do to find the cross product without using the cross product formula is to make a few observations. Observation number one is that the magnitude of I equals the magnitude of J, which equals the magnitude of K, all of which equal 1. They're unit vectors, but you could actually apply the magnitude formula and you would see that they all have a magnitude of 1. Number two, all three of these vectors are mutually orthogonal, meaning if you pick any two of them, they make a right angle. So the angle between any two of them is 90 degrees, or pi over 2 radians, if you will. Thirdly, we know that the magnitude of a cross product in general, we'll say the cross product of A and B, is equal to the magnitude of the products times the sine of the angle in between. So what does that last thing tell us? That last thing tells us that if we take any two different values here, so that the angle between them is actually 90 degrees. If you take the same vector twice, the angle between it is 0. But if we pick any two different of I, J, and K, then the angle between them is 90 degrees. Excuse me, this was not supposed to say 90. This was supposed to say theta in general. Specifically, the angle between any two of these is 90 degrees, which means that the cross product of any two of them, the magnitude, would be the product of their magnitudes times the sine of 90 degrees. But all of them have a magnitude of 1, and the sine of 90 degrees is also 1, which means if we take any two of these and form their cross product, the magnitude will be 1 times the sine of 90 degrees, which is 1. In other words, the magnitude of the cross product of any two of these is always equal to 1. Now, but that doesn't tell us which direction it goes, and that's where the right-hand rule comes into play. If we were to find the cross product of I and J, without just using the formula, we know the magnitude is equal to 1. Because the magnitude of I is 1, the magnitude of J is 1, and the sine of 90 degrees is 1. We also know that I cross J is orthogonal to I and J. Okay? So what we're looking for is an orthogonal vector to I and J that has a magnitude of 1. Well, K has a magnitude of 1, but be careful, so does negative K pointing in the opposite direction. This is where the right-hand rule comes into play. If we were to open our right hand, point our thumb out, and curl our fingers in order through I and J, then our thumb would point up, and so we know the direction of the cross product is up. So here's what we know about the cross product of I and J. Number one, its magnitude is 1. Number two, it's orthogonal to I and J, so it's either in the direction of K or in the negative direction of K. And we know by the right-hand rule that it points up, for lack of a better word. Up. So the cross product of I and J is a vector that goes up and has a magnitude of 1. Well, that would make it K. Therefore, I cross j is equal to k. Now that's a theoretical approach to justify that I cross j is equal to k. If you wanted to take the numerical approach, then you would just set up the cross product. I cross j is equal to. Now remember in class I showed you one way to do the cross product is to write the components of the two vectors on top of each other. Here's I, here's j, and then just set up the 2 by 2 determinants. For the first component, we would cover the first components and do the 2 by 2, 0 minus 0 is 0. For the second component, we would cover up the second components, do the determinant, but don't forget the negative. If we covered up the second component, come on magnet, stick, oh well. If we covered the second components, the determinant would be 0 minus 0, which is 0, then we would stick a negative on it and it would still be 0. And then for the third component of the cross product, we would cover the third components of the two vectors and find the 2 by 2 determinant. 1 minus 0 is 1. Well, look at that, it's k. I know it was probably faster to just calculate k than to argue without the components that it has to be k, but it does show you that there's more than one way to calculate some cross products. Remember, cross product is a vector just has a magnitude and direction, so if we can determine both, then we found the cross product. All right, now we could do this for every possible combination of i's, j's, and k's. I'm not going to. I am going to walk all the way over here and get an eraser. Because in this room, I'm currently using the board on the far side of the room, but I forgot to bring an eraser. All right, I'm coming back. So this is neat and all, but what do you need to know? Well, it's nice to know how to come up with the cross product, either using calculations or using analysis. But what I really want you to know, and I'll be honest, this is more for physics and engineering classes than for this class in particular, but it's nice to just know the results of cross products involving I, j, and k. So here they are. I cross j is equal to k. J cross k is equal to I. And k cross I is equal to j. It just dawned on me that I think there's a property of cross products that I may not have mentioned in class, but if you form the cross product of any vector with itself, it's equal to the 0 vector. Let me say that again. If you form the cross product of any vector with itself, it's equal to the 0 vector. Actually, that's a direct consequence of being parallel. If two vectors are parallel, the cross product is 0. A vector is always parallel to itself. So anytime you find the cross product of a vector with itself, it's equal to the 0 vector. That means that if I do I cross I, that's the 0 vector. If I do j cross j, that's the 0 vector. And if I do k cross k, that's the 0 vector. And that looks like we have every possible pair, except we don't. Because remember, cross products are not commutative. If you reverse the order, you get the opposite. So for all three of these up here, if I switch the order, I get the negatives. So j cross I is equal to negative k. Think about the right-hand rule. K cross j is equal to negative I. And I cross k is equal to negative j. And remember, I just told you these two. I didn't verify them like we verified I cross j is equal to k. I'm telling you it's the results of them. So from a physics and engineering perspective, it's convenient to have all possible cross products of i's, j's, and k's memorized. Now, that looks like a lot of randomness, but you may notice some things, such as when you form the cross product of two of the letters, you get the third one. When you form a cross product of a vector with itself, you always get the 0 vector. So really the only thing you have to remember is when does it come out positive, when does it come out negative. You could use the right-hand rule to determine that, but I have a visual gimmick that will help you. It's easy. All you have to know is your alphabet, and more specifically, the alphabetical order of I, j, and k, which is I, j, and k. If you were to write I, j, k in a row, just the letters, but then repeat it, copy and paste, copy and paste. We only need to write it twice. But if you write I, j, k in alphabetical order twice, then here's the gimmick. When you form a cross product from left to right, it's positive. I cross j is k, j cross k is I, K cross I is J. That's how I knew those. But if you do a cross product from right to left, it's negative. K cross J is negative I. J cross I is negative K. K cross J is negative I. Here it is. I think I pointed incorrectly. K cross J is negative I. That's this one. J cross I is negative K. And I cross K is negative J. That's this one. So you can actually capsulize all of the cross products involving I and J by simply writing the letters I, J, K in a row twice. If you take the product of two going left to right, it's the next one. If you go right to left, it's the next one, but negative. I cross J is K, J cross K is I, K cross I is J, going backwards. K cross J is negative I, J cross I is negative K, I cross K is negative J. I already said that one. Anyway, so it's all of those. And of course, a cross product with anything with itself is equal to the zero vector. Now, how can this help us in actually finding cross products? Well, it can help us this way. For example, let's say you want to find the cross product of these two vectors. 4i minus 2j plus k cross 2i plus j plus 3k. Now I could have written this in component form. 4 comma negative 2 comma 1 cross 2 comma 1 comma 3. You can find a cross product in IJK form by simply doing the distributive property. Distribute everything over here to everything over here. Just remember, you have to maintain the correct order because cross products are not commutative. So if I were to distribute the 4i, I would get 8 times I cross I. But I cross I is, well, let me write this down. 8 times I cross, let's try this again. Now let's use some colors here. If I were to distribute, because we do have distributive properties for cross products and addition and subtraction. If I were to distribute the 4i, then all I have to do is multiply the coefficients and figure out the cross products according to these rules. 4 times 2 is 8. I cross I is the zero vector, so we get 8 of the zero vector. 4i times j. 4 times 1 is 4, positive 4. I cross j. I cross j is k. And then 4i cross 3k. 4 times 2 is 12, positive 12. I cross k is negative j. And then we can do the same thing for the next term. We can distribute the negative 2j. But this time, as I distribute it, I'm going to figure out whether it's I, j, k, or the zero vector. For example, negative 2j times cross negative 2i. Let me try that again. Negative 2j cross 2i. First off, j cross I is negative k, so it's going to be a k vector. Negative 2 times 2 is negative 4. J cross I is negative k. Negative 2j cross j is going to be negative 2 times the zero vector, because j cross j is the zero vector. And then negative 2j cross 3k. J cross k is equal to I, so we need an I column. And negative 2 times 3 is negative 6, so we get negative 6 i's. And then one more time, we can distribute the plus k to all three of the terms over here. It's a little sloppy with the rainbows, but that's okay. K cross 2i, well, k cross I is j, so it's going to be a j. 1 times 2 is 2, more specifically positive 2. K cross j is going to be an I vector. K cross j is negative I, and their coefficients were 1 times 1, so we just pick up a negative I. And then lastly, k cross 3k is going to be 3 times the zero vector. And now we can just put all these together. The zero vectors we don't have to worry about. In IJK form, it's negative 7i. How many j's do we got? Negative 12 and 2 is negative 10. And then we have 4Ks and another 4Ks because of the double negative. So we have a positive 8K. It seems like a roundabout way to calculate a cross product, but if you know your I, J, and K cross products inside and out, then it's actually really quick. Plus, when you're distributing, you can skip any time you do the cross product of a unit vector with itself. So I could have skipped the I cross I, the J cross J, the K cross K, and just focused on these 6 over here, put them together, and then it's over with. So what do I want you to know? I'd like for you to know these. And again, the gimmick for knowing those is to write the letters I, J, K in alphabetical order. In fact, when you're doing an I, J, K cross product, it's really helpful to write this so that you can just look at it. I cross J is K, that's left to right. I cross K, going right to left. I cross K is negative J, et cetera, et cetera, et cetera. And that's what I was missing from the end of 10.4 before we started 10.5.